Long cable, thin wire, slow charge. Your EV is losing watts you paid for. Want to know where they go? Today, we decode how EV charging cable length and quality silently steal charging power. I'll show the real math, real examples, and simple fixes you can do tonight. You'll learn how much power a longer cable can waste, why cheap or undersized cables cause heat and voltage drop, and why the loss becomes big enough to matter on a 30-minute charge. By the end, you will know the exact numbers to watch for and how to stop giving away your kilowatts. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. Cables are not neutral pipes. They have resistances. Every amp flowing through that resistance makes heat and costs you power. The basic physics is simple. Voltage drop across a conductor is V drop, which is equal to the current times resistance. And the power lost as the heat in the cables is R, or resistance, times the current squared. The resistance depends on the conductor material and the round trip length of the cable. So length matters twice. The resistance R depends on the conductor material and the round trip length. Many level 2 home chargers run at 32 amps on a 240 volts. Let's do the headline math so it's concrete and impossible to misread. First, the power the charger can deliver. 32 amps times 240 volts equals to 7,680 watts. So a 32 amp 240 circuit volts is delivering up to 7.68 kilowatt to the car. Now let's show how cable resistance eats that. Engineers use typical resistance values for copper conductors. For AWG10, a commonly cited wire size for EV circuits, a good rule of thumb resistance is about 0.00328 ohms per meter. This is consistent with standard AWG resistance tables. Use that number, for example, when the exact cable spec isn't printed on the cord. Example 1. Short cable. Typical charging cable is 10 meters one way. Round trip length is twice that, 20 meters. The resistance is 0.00328. That's times to 20 meter, which is going to give you 0.0656 ohms. Voltage drop is around 2.0992 volts. Percent voltage drop is equal to 0.87%, which is under 1%. The power loss is around 67.17 watts. With a 10-meter one-way cable of AWG10 equivalent, you'll lose about 67 watt as heat, which is tiny compared with 7,680 watts input. That's fine for everyday charging. The rule of thumb, short, properly sized cable has negligible losses. Use proper connectors and good copper conductors and you are mostly fine. Example B. Long cable, 50 meters one way. The round trip is around 100 meters. The resistance is 0.00328 ohms times 100, which is going to give us 0.328 ohms. The voltage drop is 10.496 volts. The percentage drop is around 4.37%, which is above the recommended branch circuit limits. The power loss is around 335 watts. A long 100 meter in a round trip cable costs you 336 watts. That's a real chunk. At 7.68 kilowatt input, the net energy reaching the car is reduced by about 4.4%, and you're burning a third of a kilowatt in the cable as heat while charging. That matters, especially for fast charging windows, grid sizing, and safety. Voltage drop guidance commonly used by electrical codes recommends keeping branch circuits voltage drop under 3%. This is used to avoid efficiency and equipment performance issues. Longer runs need larger conductors. So the problem is twofold. Length multiplies losses. As cable length rises, heat and voltage drop scales linearly with length, but your energy loss scales with I squared. So higher current and longer cable equals to painful losses. Quality and sizing matter as well. Cheap or undersized conductors raise resistance, increase heat, and can trigger charger or car safety alerts. In practice, many public or DIY setups use longer than ideal cables or undersized runs, which turns what should be a 20 to 30 minute top-up into a longer, hotter, less efficient event. Let's unpack the real-world impact and examples you actually face. So why voltage drop matters beyond the math? A 4% voltage drop may not seem dramatic, but it means the charger or the car may see lower voltage and respond by reducing charge current or running thermal loops longer to compensate. Many EVSEs and cars monitor voltage and current. If voltage sags below expected thresholds, the charger can throttle to protect equipment. That makes your session longer and can leave you frustrated at a slow fill even when the charger says it's delivering kilowatt numbers. Tools and calculators used by electricians let installers size conductors to keep voltage drop under recommended limits. Cable construction and cooling for high-power DC stations, the cable itself is a piece of engineering. It's thicker, often liquid-cooled, and optimized to carry hundreds of amps without overheating. You can't just lengthen a liquid-cooled DC cable without derating it. The coolant flow, pressure, and heat transfer characteristics change with the length. That's why many DC fast stations keep cables short and heavy, and why extensions hacked for DC are a non-starter. Extending a cooled cable often forces lower current limits. Connector quality and contact resistance, another invisible thief. A dirty or corded connection adds contact resistance concentrated at a tiny spot. That contact resistance behaves like a resistor in series and produces heat at the connection point. Repeated high current sessions with marginal connectors will make the contact worse over time. That's one reason public chargers are maintained and why poor third-party cables can cause failures. If you see a connector running hot or smelling burnt insulation, stop using it and report it. AC versus DC cables, different beasts. AC level 2 charging uses your car's onboard charger, so typical currents are moderate, like 32 amps. The cable sizes and run lengths used for home installs are usually short and loses small. For DC fast charging, the cable carry much higher current, hundreds of amps, and therefore the same percentage resistance causes much larger losses unless the cables are thick and short. That's why DC chargers always use the shortest possible cables and advanced connectors. Don't assume that an extension or improvised cable is safe for DC charging. Real parasitics add to the story. Cable loss is only part of the invisible thieves. While charging, your car may also be burning watts for HVAC and battery thermal management, which can be several kilowatts in extreme cold or hot conditions, infotainment systems, and 12-volt loads. Studies and lab reports show thermal systems and HVAC can draw multiple kilowatts. That combined with cable losses reduces the net power heating the cells and can cause the car to throttle or pause the charging. In short, cable loss plus parasitic loads can slower your net charging. So what this means for you practically? 3 scenarios. Scenario 1. Home charging standard setup, short cables. Losses are tiny if your level 2 run is under 10 or 20 meters and you use a correctly sized circuit like 8WG for 40 amps or etc. Expect losses of less than 1%, which is negligible. This is the sweet spot for daily commute charging. Cheap, fast enough, and battery friendly. Scenario 2. Long run or undersized wiring. If your garage outlet is 50 meters from the panel and the installer used 2 small conductors, you can see 3 to 5% or more voltage drop and hundreds of watts lost in the cable. That pushes the charger or car to throttle and raises heat and safety risks. Fix. The fix is upsizing conductor, like larger AWG, bigger millimeters of the cable, which reduces resistance and brings voltage drop back into the cable acceptable range. Use voltage drop calculators electricians use to size correctly. Scenario 3. Public DC fast charging with long or damaged cables. The cable is designed to be short, heavy, and often cold. If it's damaged or someone tries to extend it, you'll either get lower peak charging power or trigger safety shutdowns. Don't try to extend or jerry-rig a DC cable. It's unsafe and quickly derates performance. Quick checklist you can use tonight to stop giving away watts. Keep cable runs short where possible. Aim for the best length of the cable for the home level 2 installs to keep losses small. Use the right gauge that the electrician size for the voltage drop as well as the ampacity. Upsize conductors for longer runs. Avoid extensions for high current charging. If you must use a certified extension, make it short, heavy, and rated for the full continuous current of the EVSE. And check local code. Never extend DC fast cables. Inspect connectors, clean contacts, avoid corrosion, and report hot or damaged public cables. Contact resistance kills efficiency and can be dangerous as well. Factor parasitic loads into your charging plan. Thermal preconditioning before a DC fast charging stop and minimizing cabin HVAC while charging reduces the combined effect of the parasitics plus cable loss. Industry studies show thermal management can change range and charging power materially.